Hello, I'm Contact from Group 5.
I'm from Junior.
And I'm Ong Yuxiang.
I'm Wong Shenjun. This is our Group 5 project.
In this assignment, we designed a digital circuit to display a specific character set which is 1, 9, N, 0, and P by using a 7-segment display. This project involves both combinational and sequential logic design. Combinational logic is used to control the individual segments of the display based on input conditions, while sequential logic is introduced to automate the input sequence. The design was enhanced by integrating a 555 timer and JK flip-flops to create an automatic counting system. This allows the circuit to cycle through the characters without manual input, demonstrating how real digital systems operate. For the logic design, the truth table was first constructed to determine which segments of the 7-segment display should be turned on for each character. The Karnaugh maps were used to simplify the Boolean expressions. Based on the K-map, Boolean expressions were derived for each segment labeled A to G. These expressions were then simplified using Karnaugh maps to reduce the number of logic gates required. Several basic logic gates were used to implement the simplified Boolean expressions. These include OR gates, AND gates, and NOT gates. OR gates were mainly used in expressions such as A plus B plus C for segment A and B, and B plus C for segment C as well. This means the output will be high whenever at least one of the input is high. NOT gates were used to generate complemental signals such as B complement and C complement. These are important for expressions like segment E, which is A plus B plus C complement. For segment F is always equals to 1, meaning it is permanently on. AND gates were used in segment G, which is given by A plus B complement times A plus C. This requires combining two conditions together so the output is only high when both conditions are satisfied. By using these basic logic gates, the circuit is able to implement the simplified Boolean expressions efficiently while reducing the number of components required. The outputs of these logic equations are then connected to the 7-segment display to produce the required characters.
Next, for the result part. When we first power up the circuit or when the reset button is pressed, all 3 flip-flops are cleared to 0. So the binary state is 0, 0, 0. All 3 LEDs are off, and the 7-segment display shows the characters 1. When the 555 timer sends the first clock pulse, the first flip-flop toggles. The binary state becomes 0, 0, 1. The LEDs for C turn on and the display changes to 9. On the next clock pulse, C toggles back to 0 and B toggles to 1. The state is now 0, 1, 0. The LEDs for B is on while C is off, and the display shows N. The next clock pulse, C toggles again to 1. Now both B and C LEDs are on, giving us state 0, 1, 1. The display shows the letters O with all segments active except segment G. On the fourth clock pulse, B and C both reset to 0 and A toggles to 1. The state is now 1, 0, 0. Only the A LED is on and the display shows the letters P. After state 1, 0, 0, the next clock pulse would bringing us to 1, 0, 1. However, we do not want state 1, 0, 1, 1, 1, 0 and 1, 1, 1 to appear. So the NAND gate detects when the state reaches 1, 0, 1 and immediately sends a clear signal to all flip-flops, resetting everything back to 0, 0, 0. The displays go back to showing 1 and the cycle repeats automatically. We also have a manual reset button here. No matter which state the circuit is currently in, pressing this button immediately clears all flip-flops back to 000 and the display returns to 1.
So I'm going to talk about the 555 timer in our circuit. The 555 timer acts as the astable multivibrator or the heartbeat of the circuit. Its job is to generate a continuous square wave clock pulse. This replaced the manual push button, which is originally our design, because the push button is unstable and often bounce signal. So by using the 555 timer, it ensures a consistent and bounce-free signal to trigger the JK flip-flop. As for the operation of the circuit, I've configured the 555 timer in astable mode. In this setup, the circuit has no stable state, so it just continuously toggles between high and low, which is 5W and 0W respectively, without any external trigger. The frequency is determined by the RC network inside the circuit. As for the components inside the circuit, the timing is controlled by two resistors, R1 and R2, which are 1 kilo ohm and 68 kilo ohm respectively, and also a capacitor, the 10 microfarad capacitor, between ground and pin 2. So the charging path of the capacitor, it charges through R1 and R2 until it hits about 2/3 of 5W at the threshold. As for the discharging path, it discharges through only into pin 7 until it hits 1/3 of the 5W, which is the trigger. As a result, this creates a frequency of approximately 1 Hz, which is ideal for observing the binary transition on the 7-segment display. Other than that, a 0.1 microfarad capacitor is also added to pin 5 to filter out noise from the power rail. As for the output, I've connected pin 3 to the NAND gate to use the NAND gate as a buffer to trigger the JK flip-flop.
Okay, now I will be explaining how our JK flip-flop works. So we are using 3 JK flip-flop in the circuit. So first, the JK flip-flop is set to be the toggle flip-flop, which the J and K is connected to VCC, the high input. And the set function in pin 2 and pin 7 is active low. So it also connects to the high input to make sure that the set function do not operate. And then, okay, now the 555 timer output is connected to the NAND gate, then to the clock pin of the first flip-flop. So the NAND gate is act as a buffer to produce a clean and accurate high or low signal. So the first flip-flop output, QC, is also our least significant output, and it is connected to the second flip-flop, the clock pin. So the second flip-flop output, QB, is our second bit output, and it is connected to the third flip-flop clock pin. And the third flip-flop output, the QA, is our most significant output. So because we just only need 5 output, which until 100, or in decimal until the 4. So to eliminate 101 and so on, the NAND gate is used. The input of NAND gate is QA and QB. So for the case 101, the QA and QB is 1. So the NAND gate will produce a 0, the low signal, to the reset in flip-flop. Because the reset is also active low, so the low input will make it reset everything and back to 000 and continue to loop again from 000 to 100. So that is my part. Thank you.